Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 13, BGP Part 1. And BGP, along with multi-area OSPF, are your major two challenges when you're facing the BSCI exam. BGP tends to be the larger challenge because most of us don't get a lot of exposure to this protocol unless we're already working for an internet service provider. So we're going to split this up into three separate lessons. This one's going to focus a little heavier on theory, and it's theory you've got to know for the exam and for the real world. We're going to get into configurations as soon as we can, believe me, and we're going to go through different network scenarios throughout the BGP videos. So we're going to build a little bit on the core that we've been using throughout the course, but we're going to continually move things around. Because what's important with this, there is a lot of theory here, and if you don't really see what's going on the routers, it's just dry theory, and it's hard to stay interested, and frankly, it's hard to retain it that way. So we're going to do with BGP what I do with every single video and every single protocol in all of my training courses, and that's show these to you in action as well as just talking about them. And the key there is to show you all the features of BGP. We're going to have to come up with several different network scenarios. So I just want you to be ready for that. We're not going to build one network and stick with it as we have with the other routing protocols. Before we get into that, though, we've got to get the basics down of what BGP is, and we'll talk about that for a few minutes in our introduction to BGP. And just as it's important to know how to apply a command to a router, and it's also important to know how to take it off, it's important to know when to use BGP and when not to, and we'll go over that in detail. We'll then talk about the basic BGP peering process, and you'll hear me call it a peering, you'll hear me call it a neighbor, you'll hear me say we've got an adjacency. They're interchangeable terms, but with BGP, you want to be prepared to see the word peer, because we tend not to talk about neighbors as much as we do peers. They're the same thing, though. And speaking of neighbors, then we'll talk about iBGP versus eBGP neighbors and routes, because that's a little letter in front of the BGP there, but it's got a big meaning, and it's going to continually affect our BGP routing. So to understand the effects that it's going to have later on, we have to know what iBGP and eBGP are to begin with. You'll see how we advertise routes in BGP. Very simple statement. And then we'll get into path attributes. Boy, 2 words and so many details. If you've done some reading on BGP in the past, you know that we've got several path attributes we've got to know for the BSCI exam and for the real world. We've got to know what these attributes mean and how to change them. And we're going to take a look at every single attribute like that you'll see on the BSCI exam, and I'll introduce you to a few that you really won't see until you go after your CCIE in routing and switching, or perhaps some of the other certification tracks for the IE. Because I want to throw this in before we hit the introduction. Even if you think you're not interested in the CCIE program, you may well be one day. And this is one of the skills, BGP, that is just a core skill for going after the CCIE. And if you look at BGP as a whole, it can be a little intimidating to get started. You're just going, wow, there's just so much here. And that's how I felt about it the first time I looked at it, because we're going to use terminology that's different, the routing's going to be different, and a lot of things are going to be different about BGP than about any of the protocols you've learned to date. So stick with it. We've broken it down into smaller parts because that's how you want to learn everything in Cisco. You learn the fundamentals, you learn the basic theory, and then you build on that. When you're building on the basic theory and you know the basic theory, you're going to pass. If your foundation is weak, then you cannot possibly learn the intermediate and advanced skills that you need to pass Cisco exams and be good with BGP. And speaking of being good with BGP, or what we use it for in the first place, it's an external routing protocol or an external gateway protocol, an EGP, used by internet service providers, ISPs. And if you don't work for an ISP, your exposure to the BGP protocol is going to be limited at best. I put a definition here for you. It's not the official definition, but it's an internet protocol that enables groups of routers called autonomous systems to share routing information so that efficient loop-free routes can be established. And that's our favorite kind of route, efficient and loop-free. And again, BGP is commonly used within and between internet service providers. This kind of runs on top of everything that you've done to date, because at the very core of our network, of course we have our physical layer, but then we've got our switches. Then you've kind of got your routers on top of that, where our interior gateway protocols run, such as OSPF, ISIS, eIGRP. Well, BGP kind of runs on top of all of that. It's an inter-AS routing protocol, because an autonomous system, which is simply a group of routers managed by a single administrative body, an AS is going to use an IGP to route packets inside the autonomous system. But for inter-AS traffic, that's where an exterior gateway protocol, such as BGP, is going to be used. Some familiar terms for you here. BGP supports variable length subnet masking. It supports route summarization. It supports CIDR. It will send full updates only when routers initially become peers, and after that will send only partial updates, of course updates reflecting the change in the network. And that sounds an awful lot like eIGRP to me. It's the same operation as far as routing updates go. But here's where BGP differs from everything we've looked at to date. BGP is described as a path vector protocol. Now what the heck does that mean? Path vector. BGP routers are going to exchange extensive information regarding routes as opposed to distance vector protocols. Because with a distance vector protocol such as RIP version 2, let's say the most advanced distance vector protocol we have, a route is pretty much a route. It's not marked with attributes. It's like, here's the route, I know about it, and that's it. But you're going to see with BGP that there are several attributes. Some by default, some that we need to configure, but these path attributes help autonomous systems make routing decisions when multiple paths between two ASs exist. There's got to be a way to choose the best path, and that's how we do it with path attributes. When we look at a BGP routing table, you're going to be surprised at how many little details are in there that are just not in there for OSPF and eIGRP and our other protocols. Because BGP does keep a routing table that is separate from the IP routing table. Now you can run show IP route, and the best BGP routes will appear in that table. But it's the BGP routing table where all of the potential routes exist, and that's what we're going to concentrate on in these lessons. But BGP does keep a routing table separate from the IP routing table. Now, when I talk about when to use BGP and when not to use BGP, these are Cisco recommendations you should know, especially for your exam. And once you learn what BGP is all about, the rules make perfect sense. So if these are a little fuzzy to you now, once you're done with the BGP lessons and you come back and review this, then I think it's going to sink in better for you. But when you should use BGP, first off, if your company is connecting to more than one autonomous system or more than one ISP, you may really want to use one path over the other. Maybe you don't want to split it. Maybe one path is just faster than the other. Using BGP path attributes can affect the decisions on which path will actually be used. If the routing policy of your company and your internet service provider differ, path attributes again can help you select the path you want your data to go through. And finally, if your company is an ISP to begin with, BGP will be needed if, and I don't use capital letters often unless it's an acronym, if traffic from other autonomous systems are going to use your autonomous system as a transit domain, then you probably need BGP. Let's talk about when you wouldn't use it, because you may think, well, we'll just use it anyway. Maybe we don't want to, because what you're going to see here is that BGP is a huge hog when it comes to router resources. You don't want to use BGP unless you have a good reason to do so. And here are some reasons that you wouldn't use it, and the first two kind of relate to each other. When you only have one connection to the net or to another AS to begin with, or you don't have a redundant link, because we always want redundancy. I mean, backup plans are the name of the game in what we do. We've got to have a Bismarck plan. We've got to have a plan B. But if you don't have a plan B, if you only have one connection, then there's no reason for you to be using a path selection protocol. Because when you have no choice, the choice is clear. And if you don't care, maybe you're in a situation where you've got multiple paths to reach a network in another autonomous system, and you couldn't care less which path is used. They're both equal to you. Then you don't want to use BGP. Because the fourth reason is the one we really have to watch. When router resources are a concern. Because as I mentioned a moment ago, and it bears repeating, that BGP is a resource hog. And BGP tables can get very big very quickly. We really have to watch that. And if you've got a router out there in a situation where you don't have a lot of CPU, you don't have a lot of memory, you really don't want it running BGP. The amount of memory and CPU you would need, simply it would be affected by how large the routing table is going to be and what the load is. So there's no way I can give you the exact amount of memory or CPU you'd need. But if your router resources are getting hammered already, adding BGP is probably not a good idea. And then finally, when you may not want to use BGP is when there is a low bandwidth connection between multiple autonomous systems. Because there is some overhead with BGP. There's an underlying control connection between two neighbors. There are keep-alives that have to be sent to keep the peering up. So if you just don't have bandwidth to spare, static routing and default routing may actually be a better choice. Because they, of course, have no keep-alives. There's no keep-alive with static or default routing. So that's a guideline, again, about when to use BGP and when not to. And I mentioned a moment ago that BGP had some network overhead, that there was a control connection. BGP is connection oriented, and that brings back our intro studies, right? When you're learning the differences between TCP and UDP. BGP actually uses TCP port 179. Don't take the exam without knowing that. Maybe you get a tattoo of it. I don't care, but you need to know that's TCP port 179. Not just for the exam, however, because sometimes when you're using access lists to block traffic, this port can get blocked with our implicit deny. I've seen it happen, and then all of a sudden people are saying, "Hey, we can't get out to the net," or "Hey, our BGP connections are all down." That's because you blocked port 179, and if you do that, your BGP adjacencies are going to die. So don't do that. Once the adjacency is established, the BGP speakers, and that's how we refer to routers running BGP as speakers, exchange routes and they synchronize their tables. And just as we mentioned, it's a comparison to eIGRP, where a BGP speaker will only send further updates upon a change in the network topology. Here is the first huge difference between BGP and the IGPs that we've worked with so far. BGP peers do not have to be in the same autonomous system to become peers. Of course, with IGRP and eIGRP, the routers had to agree on what AS they were in and the metric weights. Well, there are no metric weights here with BGP that we have to be concerned about, but they also don't have to be in the same AS. So when you're troubleshooting BGP in the production network, if you're taking the exam, you've got to be really careful not to make the assumption that, oh, these aren't in the same AS, they can't be peers. You're going to get so much practice in that it'll be second nature to you. And while they don't have to be in the same AS, whether they are or not affects what kind of peer they are. Peers that are in the same autonomous system are iBGP peers, that's internal BGP. And peers in different ASs are eBGP peers, that's external BGP. That is not just trivia. That's going to affect your routing selection, your route selection. It's going to affect a lot of your path attributes. So you've got to be careful when you're analyzing a network to see whether or not they're iBGP peers or eBGP peers. So having said that, Let's take a quick look at some Cisco recommendations for these peerings. And again, they are recommendations, and I'm going to be talking about theory versus real world a lot right here with this particular rule. Cisco recommends that your eBGP peers be directly connected. And that's fine. That's not always going to be the case. But where it says that iBGP peers generally will not be directly connected, that is true. Cisco recommends that those eBGP peers be directly connected. That's not always possible in the real world, though. That's not always possible in a production network. So later in this video, I'm going to show you how we circumvent that rule a bit, because quite a few large BGP networks circumvent that rule all the time. There's nothing wrong with it. Before we take a look at our first peering, though, let's mention the peering states here, because we'll see a few of these in action. And the first one is idle, and the speaker is waiting for what we call a start event. And the start event we're talking about there is either the establishment of that TCP connection that we talked about earlier, or the reestablishment of a previous connection. Once that connection is established, BGP will move to the next state, and that is connect. And this is where the TCP connection actually happens. It finishes. And if the TCP connection completes, BGP will move to the open sent stage. If not, it goes to active, and we're going to discuss active right now. Again, just like we talked about with eIGRP, when the routes went to active, that was really bad, although it sounded really good. Well, an active peering is not good if you see it for a long time. Because what this means is that the local BGP speaker is continuing to attempt to create a peer relationship with that remote router. And if it stays here for a long time, it's not necessarily terrible. It could just be that you just haven't gotten to the other peer to put a corresponding neighbor statement. Because one router can't peer to another without the other router peering back. It's a two-way arrangement. So if it stays in active state for a long time, it's nothing terribly wrong until you get to the other router and you put the neighbor statement on. And if it stays inactive, then you've got a problem somewhere. A little real world here. Once in a while, you'll see one go between active and connect. And active and connect, it's going to flap. This can indicate an issue with your configuration, but I have found that it also indicates an issue at the physical layer. And we never want to get too fancy with our troubleshooting. We're always starting the troubleshooting at the physical layer. It can actually be the cable itself. I have seen that happen. Finally, we go to the open confirm state. And this means simply that the speaker is waiting for a keep alive message. And once that happens, they go to the established state. And once they hit established, this is where the update packets start to be exchanged. As you're going to see, when we start putting routes into our BGP configurations, it's not going to happen as fast as you may have gotten used to, especially with OSPF and IS to IS. It's not going to be lightning fast. So some of these times when we're configuring peerings, when we're waiting for networks to show up, you can start thinking, well, did I do this right? You probably did. Just give it a few extra seconds to make it happen. So what we're going to do then is get a configuration started, a basic configuration. And you're going to see this one's real basic, where we're looking at router 1 and router 3. And we're going to build a peering connection between those two. And here's the peering that we're going to build actually to start with between router 1 and router 3. They're going through the frame relay cloud just as they did in earlier networks. And we're going to build a very basic peering. We're going to put R1 into AS100 to begin with. So we'll bring our router up here, our router screen, and go with router 1. Very basic configuration to start with. We always have to put the local AS number here. And this is the neighbor command, where you actually specify the IP address of the neighbor. And let's use iOS help here to take a look at our options. Whoa, that's a lot of options, and we're not done. Let's make the screen a little bigger. And as you can see, BGP can get pretty granular here just with the neighbor command. And that is a lot of options. Do not panic. You do not have to know all these for the BSCI exam. I remember the first time I looked at this, and I don't even think I had to know all of them for the CCIE lab. There's a lot of stuff here. So don't panic. We're going to learn them one at a time. We don't have to learn them all right now. We're not going to learn them all today. I just want you to be aware that with BGP, we're in a whole new world here as far as how granular we can get with our network, the amount of control we can put over it. All we're going to do here, though, is use the remote AS command to name the remote autonomous system that the potential neighbor is in. It's right in the middle of all this. Specify the BGP neighbor with remote AS. So that's going to be it. We're going to hit enter. And we're going to, first off, and I'll rerun that because I see that the command got in the console message got in the way. Got to get used to that too, though. Show IP BGP neighbor. This is a good command to see your neighbor relationships, but I tend to use this more for troubleshooting BGP than anything else. And I'm going to show you another shorter command. You need to know both of them for the exam, but another command that will give you a little more concise look at your neighbor relationships. But in this one, we could see where you got show IPGP neighbor. It shows what one of the neighbors is, what AS it's in. We don't have a remote RID for the remote device yet because we don't have a neighbor relationship because the BGP state is still in idle. And let's see now. It's been a little while since we ran that. It's now inactive. The BGP state has turned to active. So basically what's happening right now is this router is going to keep trying to make a peer with the remote router. But it's not going to happen until we go to router 3 and put that neighbor statement, put a corresponding neighbor statement onto router 3. So we're going to put it in BGP 200. The remote neighbor is 172.12.123.1. Remote AS 100. Good troubleshooting stuff. Good troubleshooting question. Just watch the BGP numbers. Now let's see about how long that takes to configure. Or rather to finish. It's in idle right now for 172.12.123.1. Again, you have to learn a little bit of patience here. It's still in idle state. Now it's moved to active. And that's what we want to see. We still see it in active. We still see it in active. This is about the time where you start thinking, did I do this right? Do we have another problem that I don't know about? And there we go. With the adjacency change logging message there, 172.12.123.1 up. And let's run the neighbor command again. And we can see now that the BGP state has moved to established, and it's been up for 12 seconds. Great command in case somebody's complaining about BGP connectivity. You know, I think we've been losing our adjacencies, something like that. You can run this command and see how long the adjacencies on this router have been up. So you get even more information in this command as you see. A lot of hardcore BGP stuff here in the middle. Not a lot of stuff you need to worry about right now. But notice that it is foreign port 179 that's in use on the remote device for the control connection, for the underlying TCP connection between these two devices. So as you can see, that's a lot of information, and that's just with one neighbor. All this information is about the remote router 172.12.123.1 and the neighbor relationship to it. What I like to do, just to see if a neighbor relationship is up or down, is run show IP BGP summary. And what this gives you, it gives you a neighbor table that looks a lot like some of the protocols you've worked with earlier. Shows you your local router's BGP RID, It shows you the local autonomous system number, and it shows you your neighbor or neighbors. It shows you what AS they're in, how many messages have gone back and forth. Table version, in queue, out queue, we're not concerned with now. Shows you how long the adjacency's been up or down. And that's a good thing too, because if the adjacency's actually down, it's nice to know when that happened. If you're called in or you walk into a client and they say, well, we think it's been down. Well, how long has it been down? A while. You know how that works with the end user interview, right? It's been down. It was like that when I got here, and it's been down a while. This command actually shows you how long the adjacency's been down, which can be very helpful. So at this point, we have configured a 2 router setup in BGP, and what we're going to do here in a moment is bring the 3rd router in, router 2. What we have in existence right now is an eBGP peering between routers 1 and 3. Notice with BGP as well that when you put a router into an autonomous system, you're putting the entire router into the autonomous system. With all the protocols that we've looked at earlier with our interior gateway protocols, we could, particularly with the protocols that allow us to use wildcard masks, really tie down which interfaces were enabled with that protocol. And there's no problem if you wanted to with putting different interfaces on a core router in different ASs. We could do that. But you don't do that with BGP. The entire router is actually put into the autonomous system. So again, we've got an eBGP peering here between routers 1 and 3, and that is going to come into play here very shortly. But in the meantime, we're going to go to router 1. We're going to make that peering with router 2, which is an iBGP. They're both going to be an AS100. And I'm going to show you a common error, something to look out for on the exam, because it's something that the router will not let you do. And I like Cisco routers because most of the time they won't let you do anything you shouldn't do. So we're going to make a neighbor statement here for 123.2, which is router 2's frame relay interface, 0.0 interface. We'll put the remote AS option here, and it's going to be in the same AS. And that's all we have to do. But if I had attempted to put 123.1 in here, let's see what would have happened. If I tried to put the local router's IP address in for the neighbor statement, the router will not allow me to do that. And cannot configure the local system as neighbor is just simply saying, hey, you're trying to put your own IP address here in the neighbor statement. That's all that means. Common error. We'll go over to router 2 and start a BGP process. Let's see what do you think the numeric range is for AS numbers? 1 through 65,535. It's a good number to keep in mind, what the range is. But there are some private AS numbers in there, just as there are private IP addresses. You'll definitely know what those are by the end of the course. But I want you to see now what the entire range is. 1 through 65,535. Put this in BGP 100. Configure a neighbor statement back to router 1. I hit the space bar there. And that's it. We'll go up to router 1 now. And I'm going to run the summary command, show IP BGP summary. And you can see also that if you've never had an adjacency, it's actually going to show you never right there. I like that. And you can see the state right now is active. I expect to see a log statement here in the next 15 seconds that the adjacency is up. And you can see the different AS numbers here between 1 and 2. And there's our log message that the adjacency is up. I'll hit enter to get past that, run the summary command again, and you can see that the adjacency for router 2 has been up for 8 seconds and for almost 6 minutes to router 3. So we talked about Cisco's recommendations earlier, and I'll bring the diagram up here. Again, Cisco's recommendations is that eBGP neighbors are directly connected, and they are here. Generally, that's not going to happen, though, we'll use loopback interfaces in our neighbor statements on occasion. And we're going to have a command called eBGP multi-hop that allows us to do that. Now with iBGP, we don't have to worry about the routers being directly connected. But what we do have to be concerned here with is that a potential neighbor has to know how to get to the address specified in the neighbor statement to begin with. Makes perfect sense. If we try to use router 3's loopback right now as the neighbor IP address, router 1 doesn't know how to get to that address right now because we took all the IGPs off before we started this lesson. So we'd have to put a static route in. That could help. But keep in mind, when we're putting these neighbor statements in there, they're not working by magic. The local router has to know how to get to the IP address that you're putting in there. And here, there was no problem because we're using the network that we've got on the directly connected frame relay. They're directly connected to that subnet. Now let's take a look at how we advertise routes in BGP. And this is another thing that you can do, and it takes a few seconds for the routes to show up downstream, and you start thinking, did I do this right? With BGP, sometimes the hardest thing with the basic configurations is being patient. So don't think, hey, it didn't show up in 4 seconds, I must have done something wrong. Give it a little time to cook in a way. We're going to use the network command in BGP, but not quite in the same way that IGPs use it. And this is going to sound a little like splitting hairs, but it is an important detail. The BGP network command identifies the networks that BGP will actually be advertising. With IGPs, the network command identifies the interfaces that will be enabled with that protocol. So when we put in here network 3333, we are not enabling BGP on router 3's loopback. We're advertising it. So let's do a quick show config here. And I've got a couple of loopbacks on here. And we're going to use that loopback 0, the 3333. And notice that it has a 32-bit mask. So we're going to go under the BGP process, which right now is router BGP 200. We're going to use the network command to advertise that network. Let's see if the route ever shows up. I'm going to use a command BGP. What I did there was I cleared the BGP routing tables with what we call a soft reset. It's clear IP BGP asterisk followed by soft. It's an excellent command to know for the exam in the real world because this has the effect of clearing the BGP routing tables without clearing the connection itself. Because if I type clear IP BGP asterisk and then hit enter, my adjacencies will actually be torn down. We'll take a look at that in a few minutes. It's not that I'm scared to use that here. We're in a lab, so you want to experiment as much as you can. But in a production network, I would use this. And the same goes for the exam. It's a good idea to know the command that resets the tables without tearing down the connections. What you'll find, though, and we may see this on a router in this particular rack, that not all routers can use this command. Not all routers are capable of a soft reset. Some earlier iOS versions may not be, and some other router models may not be. It generally comes down to the iOS. We may see that here. So let's go over to router 1 and see if we see that network. We don't see anything, and there are actually 2 tables here. Show IP route BGP is going to show me any BGP routes that are in the IP table, but the table that we're going to be most concerned with in this lesson and throughout our BGP studies is the BGP table itself. That's where the path attributes show up. That's where the multiple paths show up, and that's where we do most of our work with BGP. However, there's no work to do here because there are no routes. Common error here, and I did this on purpose. We took a look up here at the loopback 0 interface, and then we put in the BGP command. Notice that this is a network with a 32-bit mask. And you're not going to see that except on a loopback interface, but that's why I did it. This network statement has to match that exactly, or it's not going to advertise it. So this is a very common error. Putting this network in doesn't match what's on the interface as far as the mask goes. So we've got to put in network 3333 mask 255 and then forward from there. Very common error. We'd rather see them here than on the exam. We're going to take that network statement off. And put this one on. Notice that this is a network mask. It is not a wildcard mask. We don't use wildcard masks for network statements in BGP. We're going to clear the connections softly. I hate it when the config command comes up like that, the console message. We'll do a quick WR on the way out to router 1. Let's give router 1 a little time here and see if it sees the route this time. We think we did it right. See, with most of our IGPs, we'd already be seeing the route by now, but BGP is not going to be that fast. And of course, being patient is not always easy in our business. Especially when you're sitting there thinking, did I do that right? Did I do that configuration right? You probably did it right. You've just not given the router enough time to catch up, basically. And there we are. So you saw there it actually took about 20 to 25 seconds for that route to appear. So let's take a look then at this particular route and the path attributes that we're going to see. Because you've got to know what all these symbols mean. And we've got a lot of different stuff here that we just haven't seen in other routing protocols. Let's take a look at what some of that is. We've got this asterisk here for valid. We've got an arrowhead or a greater than sign, I don't care what you call it. Best, best what. Here's an I for internal. Here's some origin codes. Not real sure what those mean yet. And we've got another one. We've got an asterisk and an arrowhead down here. And we've got a network, a next hop, metric, whatever that is, a lock perf, a wait, and a path. We got to know what all this stuff is. You have to be able to look at this table and just say immediately, here's what that metric means, here's what that wait means, here's what that path means, and here's what all this stuff means, because you are going to be so good at this that the BGP questions on the exam will not bother you a bit. So let's talk about these path attributes. And we're going to continually revisit just the little baby network was set up here. Because again, notice that this is what we've got. And it's not a bad idea for you to jot this down while we're going through this discussion about iBGP and eBGP. We've got two peerings. We've got a peering between R1 and R3, a peering between R1 and R2. R1 and R2 have an interior BGP peering because they're in the same AS. And routers 1 and 3 have an eBGP peering because they are in different autonomous systems. Now, for the BGP path attributes, pardon me. For the BGP attributes, let's take a look here at our next screen, and we're going to look at these one at a time. There are several you need to know inside and out for the exam. We're going to look at them one at a time. We're going to go over the theory, and then we're going to keep revisiting that routing table that we just created to see these things in action. The origin attribute shows you the source of the routing update itself. There are three possible values for the origin code: a lowercase I, a lowercase e, and a question mark. And this question mark has nothing to do with iOS help. Nothing. So let's take a look at that table that we just had. And we've got an I at the very end of that. And that's our origin code. And it's going to follow the path. You'll notice that there is no origin column, so you've got to know what that is. This indicates that the path was originated with the network command. The code actually stands for IGP. And since we started it with the network command, it's going to have the I for an origin code. If it had an E, that means it was originated by an eGP. And then finally, an origin code of a question mark means incomplete. Well, what does that mean, an incomplete origin code? What that means, excellent exam question, excellent job interview question. What that means is the route was learned most likely via redistribution. What it really means is BGP doesn't really know how the route originated. It's still valid, as we're going to see, but the BGP process says, oh, I don't really know how this originated. I don't know how this path originated. So that's what the I, the E, and the question mark mean. And the reason I put them there in that order is that that is the order of preference, from most preferred to least preferred. If the origin code is being used for path selection, then IGP is preferred, then eGP, and then finally incomplete. The AS path attribute can really be helpful in troubleshooting larger BGP scenario, deployments. And this attribute can also be seen with the command show iBGP. We're just going to keep coming back to this table and this command. This is why you don't look in the routing table. Let's take a quick look at the routing table right now for BGP. And see, that's not really telling us anything. That's the route that is in the IP routing table right now. And you will see them here. They're in the middle. This one, they're marked with the letter B. And you'll see them in the IP routing table. But obviously, this is not going to help us much with path manipulation. It's not going to help you much on the exam either. If you want to see the path attributes, you've got to run show iBGP. And what this attribute does is it shows the autonomous systems that are along the path to the destination network, including the autonomous system that the destination network resides in. And in this one, you can see that the path, and that's what the path refers to as AS path. The path here is very short because there were no intermediate paths or intermediate autonomous systems between routers 1 and router 3. So the only value we're going to see for the AS path is the actual AS that this network resides in, which we know is AS200. There's another very important use for this attribute that people tend to forget about, but you're not going to forget about it. The AS path attribute also helps to prevent routing loops between eBGP neighbors, because the larger your deployment gets, the bigger the chance that a router is going to get a route that contains its own AS in the AS path. Well, that indicates a loop. So what happens is that if a BGP speaker receives an update and sees its own AS number in the path, that route is discarded. The router will not accept it. So we've got a pretty short AS path there, but we want to go to the next level of that. We want to see some more AS paths in action. So what we're going to do is actually reconfigure the network. We're going to go with this deployment, and you can certainly jot these down if you wish, and I've got a network diagram for you. What I'm going to do is connect routers 1 and router 5 over an Ethernet segment on the network that I show you, 10110. Routers 1, 2, and 3 will continue to be connected through the cloud. Routers 2, 3, and 4 will be connected to the Ethernet using 172.12.234.0. And routers 3 and 4 will be connected. They are now connected by directly connected serial interfaces, and they're going to use 172.12.34.0. If you give me just a moment here, find that actual configuration. Here's what the setup's going to be. So I'm going to take just a moment here and get that network set up, and then we're going to look at a more complicated AS path scenario. And now the network has been successfully changed over, so I'm going to give you a tour of what I've changed on each router and what the logical setup, the BGP setup, is actually going to be. If you give me just a moment here to find that. And there we are. So this is the BGP setup that we've got on the network now. The segments changed a little bit. As you can see, routers 1 and 2 are in AS100. They're peering. Router 3 is going to be in AS300 all by itself. Router 4 is in AS400 all by itself. And router 5 is in AS500 by itself. So let's take a quick look at the router configurations. And there was nothing complex about this particular configuration at all. We'll just do a quick show config and go down to the BGP section, which is going to be down here near the bottom. And we've got a couple of neighbor statements right there. And what each router is doing is advertising its own loopback interface. So that's all I did there, was change around a couple of neighbor statements. We'll do the same for router 2. We'll take a look at each one. Nothing unusual here. You can see that router 2 is peering to router 1 in AS100, and also with routers 3 and 4 over the Ethernet segment in their respective ASs. It's going to look pretty much the same on the other 3 routers. It's a little longer here on router 3. We've actually got 5 peerings going on, and it's advertising its loopback network. So you can see the beginning, just getting the adjacency started, is not particularly difficult, but you have to know the right show commands in case there is an issue. Same thing on 4. We'll go to router 5, which has a single peering, I believe. It does, over the Ethernet with router 1, and it's an AS500 all by itself. So just bringing that right back up just for a moment, this is our scenario right now. Routers 1 and 2 are peering in AS100, and the other 3 routers are all in ASs by themselves. And you saw the peerings that we had there. What we're going to really look at here, though, is we're going to concentrate on router 1's table, its BGP table, because it has at least one entry now for every loopback in the network and multiple paths for most of them. And one thing to keep an eye out for here, that 0000 always catches our eye no matter where it is, with static routes, default routes, that kind of thing. If you got a next hop here of all zeros, it means that that's a local network. There is no next hop IP address for it. You're already directly connected to it. And we can see there's an entry for router 1's loopback. And notice the weight here. We're going to discuss the weight attribute here in a few minutes. But just keep in mind for right now, you'll see every other path has a weight of 0. By default, the weight is 0 unless the route is locally originated, which this is. We're on router 1, and that's where the network is. Locally originated routes are always going to have a default weight of 32,768. So, taking a look at that, let's examine some of these symbols that we started learning about earlier in the video. And you can see that some of the paths have an asterisk and an arrowhead next to them, but others just have an asterisk. For it to be the best path and be considered valid, it's got to have the asterisk and the arrowhead next to it for the path to be usable. That's another common error. Watch out for it on the exam, and watch out for it in the real world, because you would think, oh, well, it's got an asterisk right next to it, so it's a valid path. Well, it's a valid path, but it's not being used. Here we've got 2 different IP next hop addresses to get to router 3's loopback. And the one with the asterisk and the arrowhead next to it, that's the path that's actually being used. Before we go on with the attributes, let's take a look at the BGP path selection process. And this is one of those things that you really need to work with BGP as much as you can in a home lab environment before you take the exam, just to get this down, just to get used to it. I'm just going to tell you point blank, you have to know this chart. You have to know this chart to pass the BSCI exam, and really to be able to figure out and troubleshoot BGP in a production network. If BGP is presented with multiple paths to a destination, it's got to have a selection process, and you can see here a couple of attributes that we've already talked about, a couple that we will continue to discuss in this lesson. But this is where path attributes come in. It helps BGP select the best path. And we're not stuck with this. We can change values, and that's why we're going to keep moving to different network scenarios so you can see these values being changed. But right off the bat, the one at the top is that the path with the highest weight is going to be preferred. And weight is a Cisco proprietary BGP attribute. So if we're in a multi-vendor environment, then the first criteria is going to be the path with the highest local pref. That's short for local preference. And the way I have local pref and AS path written throughout this course, that's the way you're going to see it in BGP documentation. If those two are the same, then the path that originated locally is going to be preferred. If a path originated on the local router, that path will then be preferred. If those three values are the same, then it's the shortest AS path. If the AS path length is the same, then the path with the best origin code is going to be preferred. And again, the order there is IGP, eGP, incomplete. That's what the question mark means. If those five are tied, then we're going to look at the lowest multi-exit discriminator, or MED. We will discuss that in just a few moments. Then, if those six are ties, an eBGP path will then be preferred over an iBGP path. That may be a little counterintuitive. When I first started studying BGP, I would assume that an interior path would be preferred over an exterior path. It's actually the opposite. Then, the path with the lowest IGP metric to the BGP next hop address will be used. If all of those are the same, then the most recent path will be used. And then finally, if it's still a tie, the path that's coming from the router with the lowest BGP RID is going to be selected. I would have this table memorized dead to rights before I took the BSCI exam. So let's take a look at our routing table, and maybe we can spot something a little funny going on. Maybe. Because we see, again, I want to remind you that the arrowhead indicates the path that will be used to reach that particular network. And for more information on a particular network, you can use show iBGP with the network number right after it. And if you're looking at that, you may see something a little askew here, but we'll take a look at that in a few minutes. Right now, we're just going to look at that BGP routing table. Because there's something a little odd here with router 1's path selection for the networks 3333 and 4444. And right now, let's just concentrate on the two routes that this router has to the loopback on router 3. I'll highlight those so we can keep those in mind. Now, BGP has identified them both as being valid, and when we say valid, when we see that asterisk, what we really mean there, it's free of routing loops. That's the validity test. So it's free of routing loops and it's valid, and we see that asterisk. Now, the arrowhead indicating the best path is next to the path with the next hop, 172.12.123.3. But let's figure out why. And we can go back to our table here and we'll bounce back and forth. What's the first criteria in BGP best path selection? It's weight, right? The path with the highest weight. Weight is a Cisco proprietary path attribute, but you'll be glad to know that these are all Cisco routers. So that wait is going to be the first one we use, and it's the same. We can see under the wait column, which is the next to last, going from left to right, that the wait is 0. Now, the next criteria that we're looking at is local preference. Local preference is number 2. Well, what we see here in the table is that the path with the next hop of 234.3 has a local pref listed of 100. But there is no local preference for the path that's actually going to be used, the one with the next hop of 123.3. So if that is the case, and the path with the next hop of 234.3 has a local pref of 100, and the other path has a local preference of 0, and we're making an assumption there because we just don't see anything, then why is the path with the lowest local preference being selected by BGP when the path selection process says it should be the highest? I'm going to answer that question in just a second, but let's take a look then at the routes to the loopback on router 4. See if we see anything odd there. Again, we've got 2 valid loop-free paths to this network, as indicated by the fact that both of them have an asterisk on the far left. So BGP's got to choose the best path. It's going to go through that best path selection process again. The weights are the same. The local preference seems to favor the next hop of 234.4, doesn't it? Because you see a 100 there, but you don't see a 100 next to 123.3. You don't see anything. It's kind of odd. We don't see anything. But even if the local preferences were the same, what's the next value that gets considered? Located locally, or locally originated, I should say. Well, neither one of them were originated on this router, so that's out. So then we go down to shortest AS path. Well, the route with the shortest AS path is clearly the one with the next hop of 234.4, but again, that path's not being selected. So we would look at this routing table and then look at that table of the best path selection and say, what's going on here? The command that I gave you a sneak preview of a few minutes ago is one of the most valuable commands you will ever run with BGP. It's going to serve you well on the BSCI exam. It's going to serve you well on your CCI routing exam and your lab and any job where you ever work with BGP. And first we're going to look at, well, let's run them together. We're going to run show iBGP, the loopback for 3, and then we're going to do the exact same thing right under it. We'll give ourselves a little room here. I like to do this. It's up to you in your lab, of course. We see a word in there that we really don't like in this business very much. And let's take a look at that. We hate that word, right? We hate that word in this business. Inaccessible. And we see the same thing, and it's the 234.3. The route from 234.3 with that next hop is inaccessible. And we see the exact same thing here for the route that we thought should be used. It's marked as inaccessible. Also notice here, remember we thought the local pref for one was 100 and the other was 0? That's not the case. In this one, for the network loopback for 3, the local pref for both routes is 100. And the same goes for the loopback network on router 4. The local pref is 100. So don't always trust the show iBGP table. Take it to the next level and look at the show iBGP command using the network number. Because the local pref, when there's nothing there, you tend to think it's 0, but it's not. This next hop is invalid of 172.12.234.3 and 234.4 because router 1 doesn't know how to reach that segment. We're not running an IGP here. So if we attempt to ping 172.12.234.3, we going to get anything back? No, the only thing we get is a chance to practice our escape sequence, which is Control-Shift-6, Control-Shift-6. If we try to ping 4 on that same subnet, we're still not getting anything. If a router cannot reach the address listed as the BGP next hop, the path cannot be used. It will not be valid. You'll still see it in the BGP table. Remember, we had no trouble seeing those paths. But as a CCNP and as a network administrator, as a network troubleshooter, you've got to be able to look at that and say, okay, I know the best path selection process, and something's a little screwy here. What's going on? I can tell you that maybe not 9 out of 10 times, but 8 out of 10 times, it's going to be a next hop problem. The router can't reach the address listed as the next hop. So we've got something, we've always got a workaround. And what we're going to do is use a command called BGP next hop self. And what it does is it forces a router to announce itself as the next hop IP address of all the paths advertised to the specified neighbor. So we're going to go down to router 2 and do this. Let's take a look at our drawing again, because 2 and 1 have a peering there in AS100. So we're going to go down to router 2 and configure the next hop address. Now take a look right now before we change this of what the next hop IP addresses are for those 2 loopbacks. Now we're going to go down to router 2 and go under the BGP configuration, and we're going to use another one of those neighbor options. Remember all those that we saw earlier? Let's use iOS help again and see all those choices. The one we're going to use is next hop self. R2 is telling this neighbor, I am the next hop IP address for all routes that I send you. It's an interesting definition here, though. Disable the next hop calculation for this neighbor. If you don't know what the next hop calculation is, you're going to know it by the end of this course. But we're going to disable it right now because obviously we don't like what it's doing. And then we'll talk about what it's doing. That's all there is to it. I would go ahead and do a soft reset here. Console message got in the way. Clear iBGP asterisk soft. And this is what I was talking about earlier. Notice it says inbound soft reconfig for 234.4 not possible, as it doesn't have refresh capability nor inbound soft reconfig. The iOS on that I put on there does not have that capability. It's not an old iOS by any means. But you're going to see this once in a while, and I wanted you to see it here in the lab before you saw it out in the field. Let's go to router 1, though, and see if it took place with router 1. Yep, sure did. So now we've got a couple of different values that are going to show up here. And what's going to happen is, you notice now that the loopback networks, their next hop IP address changed. All of a sudden it's got a 123.2 here. It's announcing itself as the next hop. Let's run show iBGP with the 3s after. It becomes a little more clear. You can see now that 172.12.123.2 is the next hop for this particular path rather than the one on 234. And you no longer see the word accessible here. You see who's advertising it to you. Same thing will be true for router 4, or router 4's loopback here. You no longer see the word accessible because the next hop IP address has actually changed. So let's go back to our show iBGP table then. And take a look at the table here And what we're also going to do, perhaps, is do a soft reconfig here. Make sure the routing table's got its latest information. So we'll do a soft reconfig. We see again that router 5 is not allowing us to do that, but we don't really care about router 5 right now. Well, let's run show iBGP again and see what we see. And we're going to do the same on 3 as well. And actually, we'll take a look at the differences. We'll do that in just a few minutes about the differences between just clearing it, period, and clearing it softly. And you can see again, it's basically telling us router 4 can't do that. Because not everything out in the field, unfortunately, is going to be the latest and the greatest. We wish it were, but it's not. Okay, I have now successfully changed the network configuration around a bit so we can see the longer AS path values in operation. And let me show you an illustration of what I've configured. And we're going to go to each router and take a look at it. But here, routers 1 and 2 are in AS 100. Routers 3, 4, and 5 are in their own ASs. The arrows indicate connections, not peerings. That's what I've done is taken the AS assignments and put them over the physical topology of the network. So before we take a look at the router's configurations, I've added a little column here as far as the peering relationships go, and you might want to jot these down as we go along. Router 1 has 2 peerings. It's got one to router 5 through the Ethernet, and then 2 other peerings to routers 2 and 3 through the frame. Router 2 is peering to R1 through the frame and 3 and 4 through the Ethernet. Router 3 is peering to R1 through the frame, 2 and 4 through the Ethernet, and also another peering to R4 through their direct serial connection. Router 4 is peering to routers 2 and 3 through the Ethernet and also to router 3 through the direct serial connection. And then finally, our lonely little router up there, number 5, in the AS all by itself, has only one peering, and it's peering to router 1 through the Ethernet. And if you just keep those IP addresses in mind as we go along, there's not going to be anything here that's confusing at all. Let's take a look at the routers then. And we'll hit return to take a quick look at some configurations here. Nothing here unusual. What you saw earlier with the neighbor commands, that's what I've done again here. You can see under the BGP configuration that I've put the line BGP log neighbor changes. That's the default in a lot of BGP deployments, in a lot of iOS versions. That's why we're seeing the little note come up saying when we have a neighbor and when we lose it. We've got 3 neighbors, and we're advertising the loopback. You'll also note there's a line there now that you didn't see earlier called no synchronization, and we will talk about the rule of BGP synchronization in another segment. We can't do it all at one time, but suffice to say, it's a handy command to go ahead and put in, especially in a home lab. Production networks, it's going to depend, and we will definitely discuss that in a later part of this course. On router 2, again, I've put no synchronization, or as it's often referred to, no sync. I'm advertising the loopback on 2, and there are our 3 peerings. And we'll just take a quick look around, do a show config. I don't have any additional commands configured as of yet. Router 3 is an AS300. It has 5 peerings right now, and the network is being advertised as it was earlier. We take a look at router 4, and we've got no sync configured again. It's a good idea to either have no sync on all your routers or none at all. And we're advertising the loopback. And then finally, we'll go up to router 5, take a look at the configuration I put there. And there's no sync. We're advertising the network, the loopback. And we are having a single neighbor peering, and that to router 1. Just a word to the wise here as far as home lab configurations go and home lab practices. when you're working with BGP, you want to come up with as many different scenarios as you can, and that's why I've created so many different ones for this course, so you can see all of the attributes in action. We can do route aggregation later. You can see all the BGP features you're going to need to pass the exam. But when it comes to having an existing configuration and then changing it to another network topology for BGP, what I like to do is just remove the BGP configuration entirely from every router and then just start again, because you'll drive yourself crazy trying to say, okay, now this one was an AS200, let's put it in AS300. You'll also start getting error messages from the router about every 10 seconds saying, hey, you're messing up, you got this guy pointing to the wrong AS, you got this neighbor statement in the wrong AS. You really don't want to go through that. So my recommendation to you is what I did here. I just removed the previous BGP configuration and went from scratch. So now taking one more look then at our current setup, and the table that we're going to concentrate on here to see the BGP attributes at work is router 1, because router 1's kind of at the core of the whole thing. So let's go up to router 1 and take a look at its BGP routing table. And we've got a lot more routes here, obviously. We see 5 loopbacks there in the left-hand column. One thing I'd like to point out now is anytime that we see 0000 anywhere, that tends to catch our eye, doesn't it? I don't care if it's frame relay inverse ARP mapping, or a static route, or a default route, or here, a next hop of zeros tends to make us think that something is wrong. Well, nothing's wrong here. It's just that this particular network is locally originated. That is the local router's loopback. So don't be thrown by next hops of 0000. That simply indicates that that is a local route. Now, obviously, the stakes are raised here quite a bit, because all of a sudden we've got some routes with an asterisk and an arrowhead. We've got some routes with just an asterisk. And this is a vital detail of BGP for your exam and for the real world. You've got to know what these combinations mean. The asterisk, as you can see in the BGP status code table there, it's the third line down from the command itself. It just says the route is valid. And what we mean there, if it's valid, that means it's loop free. There is no routing loop involved here. And we've also got an arrowhead there indicating best. And for each of the networks that we have 2 paths to, and that's the loopback to 3 and the loopback to 4, we have 2 paths for the loopback to network 3. One of them has been chosen as the best route, but they're both seen as valid. We've got to know why one of these paths has been selected over the other. And the same goes for router 4. Router 4's loopback, there are 2 paths, and if you are familiar with the BGP best path selection process, you may be looking at this and saying, maybe something's a little off there. Maybe it's not quite what we would expect. And it's not. And what we're going to do to see why that's the case is to take a look at the BGP best path selection process. And I know this is a long process. I mean, we've got 10 steps here. You must have this selection process down cold before you take the BSCI exam. If you do not know the order of this right off the top of your head, you're not ready for the exam. But once you work with it some hands-on, once you see these videos, it's going to come to you very quickly. You also have to know this to be effective to troubleshoot BGP and configure it in the real world. You got to know this stuff. And the first criterion, when we talk about best path, we're talking about situations where BGP has multiple paths to a remote destination. And that's what happened here. Again, we've got 2 routes to router 3's loopback and 2 routes to router 4's loopback. So that's what we're concentrating on right now. So BGP has already made up its mind. But we need to know the path selection, not just to pass the exam, and don't get me wrong, that's important, but we need to be able to look at this table and say, here's why this is happening. because as we may see, we may find out that it's not quite the way we might want it or would expect. And let's take a look at why that's the case. Right off the bat, the first criteria for BGP best path selection is highest weight. We haven't talked much about the weight attribute yet. We're going to. You'll see it in the table, but two key elements right now of the weight attribute. First off, it is Cisco proprietary. You'll never escape that phrase. You thought you were done with it with CDP, but you're not. It's Cisco proprietary. If you have what we like to call a multi-vendor environment, then this attribute is not even considered because the non-Cisco routers don't understand it. Then, right after that, we've got the highest local pref or local preference. And I've written a couple things like local pref and AS path this way because that's the way you tend to see it in BGP documentation. I want you to get used to it now. But if we are in a multi-vendor environment, then the highest local preference will actually be the first criteria considered. If those two values are the same, we drop down to criteria 3, preferring the path that originated locally. And we saw that on router 1, where one of the paths actually did originate locally. It was the path to router 1's loopback. If those three are the same, we drop down to 4, prefer the path with the shortest AS path. And we're going to see that in action here very shortly. Then the 5th criteria is to prefer the path with the best origin code. And by best, we mean this order. I, and then E, and then finally the question mark. That's the order best to worst of the 3 origin codes. After that, we're going to prefer the path with the lowest multi-exit discriminator, or MED. And boy, that sounds complicated, doesn't it? Multi-exit discriminator. It's very simple. And we're going to see that in action here shortly as well. If the MED is the same, we're dropping down to criteria 7 to prefer any eBGP path over an iBGP path. And I see people get this one backwards fairly often because I think it's intuitive to think, well, an interior path would be preferred over an exterior path. It's not the case. An eBGP path is preferred over an iBGP path. If those 7 criteria are all the same, the path with the lowest interior gateway protocol metric to the BGP next hop will be preferred. Finally, if we drop all the way down to criteria 9, we're looking at the most recent path. And then if all of those 9 criteria are the same, and it happens more often than you think, the router sending this path with the lowest BGP router ID or RID is going to be the selected path. We really don't want to leave it up to that. But again, you need to know this order to master BGP for the workplace and for the exams. So for those of you who go on to the CCIE, BGP is a core topic. You got to know it, and you got to know how to manipulate paths. And you can't manipulate paths if you don't know what the selection process is. So now, let's worry about the CCIE later and get back to the basics here with router 1's routing table. So again, the arrowhead indicates the path that will actually be used. And we're going to cut it down right now to just look at router 3's 2 possible paths. They've both been marked as valid here in the BGP routing table. But maybe there's something a little odd about it. Let's take a detailed look at these 2 paths. We see that the arrowhead is next to the path with the next hop of 123.3. How did it make that selection? Well, what's the first criteria for best path selection? It's weight. And the weight of these routes by default is 0. You notice that the locally originated route, the one at the top, has a different default weight. It's a 32,768. But the first criteria for these 2 paths is weight. They're both 0, so that's not it. We drop down to number 2. And the second criteria, you remember what that was? The highest local preference. the highest local preference. Well, the route that's been selected doesn't have anything next to under the local pref column. Notice that? Here's the path we're using, and it's got nothing under local preference. So the assumption would be that it's 0. So if we make that assumption, we'd look at the path that it's not using and say, okay, well, this one's got a local pref of 100, the other one's got a local pref of 0. Why is it being preferred? That's an erroneous assumption about the local preference, as you're going to see in just a moment. But before we go into that, let's look at the routes for to router 4's loopback. Got kind of the same thing going on here. We've got 2 valid loop-free paths to that network, and BGP now has to choose the best path. First criteria, Cisco proprietary, is wait. That's the same. We see a 0 next to both of those. So then we drop down to the local preference. And again, the path that's being selected, the one with the arrowhead, doesn't have anything under local preference. The path that isn't being selected does. It's got one of 100. So if we make the assumption, pardon me, that happens once in a while with highlighting. If we make this assumption that router 1's, there we go. If we make that assumption then that the local preference of this particular route is 0, according to that order, it should not be selected. But it is. And if we furthermore, let's say we go, okay, the local preferences are the same for these 2 routes. Let's make the assumption that the local pref is 100, and it is the correct assumption, by the way. Well, what's actually happening then, what's the next criteria? The next criteria after local preferences prefer the path that originated locally. Well, neither one of these originated locally. So then we drop down to 4, which is the path with the shortest AS path. Well, which one of these has the shortest AS path? The one that's not being used. Because the path that's being marked as best for that network has a longer AS path than the one that's not being used. So something's a little off here. Because maybe you've looked at this selection process before and maybe you haven't. But if you have, and you're a little familiar with it, and you look at that table just like we did, and that's the kind of thing we've got to be able to do. We've got to be able not just to configure it, but to look at this table and say, okay, why is this path being chosen? And if we're not getting the path chosen that we think should be, what's going on? Well, what's going on is that there is a command that I'm about to show you that's going to serve you well on the BSCI exam. It's going to serve you well on the CCI exam and lab. And boy, it's really going to help you anytime you work with BGP. Whenever you look at a BGP routing table like this and you're even slightly questioning the route selection, take a look at the BGP routing table. Got a little highlighting thing going on there. Let's get rid of that. Take a look at the BGP table settings for the exact route. And notice there that I put show IP BGP and then followed it with a network number. And even if this is the first time you've ever looked at this command, there's probably a word here that is jumping out at you that is a very bad word when it comes to networks. Inaccessible. This is the next hop IP address that isn't being used. This is the path that is not being used. And it's got inaccessible, because you'll notice the path that is being used at the very end of all this, it's marked as best. So before we look at that, let's run the same command using router 4's loopback. Same thing. We've got inaccessible here next to the IP address of this path, the next hop IP address. And this is the only command that will show you this particular information. And this is very important. Now you'll notice that the local prefs, we were wondering, well, what is the local pref of this route that doesn't have anything next to it? The local preference of these is all these routes is 100. That's the default. Don't trust what you see in show iBGP. Always run this command and double check your local preferences. But here's the key to what we're looking at right now. These next hops are invalid to router 1 because router 1 has no IP connectivity to that IP address. Let's just take a look at the routing table. We don't have an IGP running, so there's no match here in this routing table for 172.12.234.0. See, nothing there. So, of course, if we try to ping that, all it's going to do is give us practice in aborting our pings. Control-Shift-6, Control-Shift-6. Works like a charm. But that's not really what we're interested in. We want to give router 1 a better picture of the routing of the network, and it should be using .2, its neighbor router 2 as the next hop for those addresses. So let's change something here. What we're going to do is force router 2 to give router 1 a reachable IP address for the next hop. And what router 2 is actually going to do is give router 1 its own serial interface IP address as the next hop. And we do that with the next hop self command. We're going to put that on router 2, go under the BGP process, and configure neighbor 172.12.123.1. Well, remember all these? And again, we don't have to know all these for the BSCI exam. But there's a reason I wanted to show you this right here. Here's the next hop self, and iOS help is just great because I don't care what anybody tells you. Nobody can remember all these commands. We're all going to forget something sooner or later. Disable the next hop calculation for this neighbor. That's a pretty strange way of putting it, except that there is a bit of a next hop calculation for this neighbor for routes that are going between ASs and routes that are not going between ASs. And we are going to look at that later in this course. But for right now, we're concerned with just giving router 1 a reachable IP address for all routes being advertised from router 2 to router 1. So right now, what router 2 is going to do is send its own IP address, its own serial IP address, as the next hop address for all BGP routes it sends to 123.1. And if you haven't seen this in action before, you'll be really surprised at the routing table that we see here. I don't know if we'll see the changes yet or not. Okay, we have. You can see that the next hops are dramatically different here. You don't see those 234.3 and 234.4 addresses anymore. What we see instead are the next hops 123.2 for those two particular routes. These previously had IP addresses that router 1 could not reach. So let's run the show iBGP commands again, looking at those particular two destinations. And you'll notice now that the word inaccessible rather, isn't here anymore. That's what the next hop self does. It gets around the accessibility issue that we sometimes run into. And if we just repeat that command, 4.4.4.4, then again we see, looking at the two routes at the bottom, that there's no longer the word inaccessible, because router 1 can ping 172.12.123.2 all day long. It has IP connectivity to that. So let's take a look then one more time at that BGP routing table and really hammer this home, because there's something else a little different here you may have noticed. For the network 4.4.4.4, the next hop IP address that's now being used is 123.2. That changed because its AS path is shorter than the one it's getting from 123.3 as a next hop. So that did change. But the path for the destination to 3.3.3.3 the next hop is still 123.2 because the weights and the local prefs are the same, and none of the routes originated on R1. The AS path length is the same. The origin code is the same. The MED is the same. And the next criteria in line is that an eBGP route is being preferred over an iBGP route. And remember that in this diagram, R3 is an eBGP neighbor. It's in another AS. Where router 2 is an iBGP neighbor. So that's why the path selection is what it is right now. That actually came down. What number of criteria is that? That's number 7. The path selection between the two paths to the loopback on router 3 actually went all the way down to number 7. That's why you have to know this order. It's not always going to be right at the top. It's easier for us to change the weight, obviously, or the local pref, but sometimes the network circumstances are going to make you use one of the lower values or further down the path for best path selection. Now, speaking of that next hop attribute, and we were just looking at that, we talked about it a bit, but there are some specific rules for determining what the next hop IP address is. And it's very different for eBGP routes and iBGP routes. When a BGP speaker receives an eBGP route, the next hop attribute is set to the source address of the router in the remote AS that sent the route in the first place. And that makes perfect sense. But for iBGP routes that were originated outside the AS, the next hop IP address is still the source address of the router in the remote AS that sent the route advertisement. Pardon me for misspelling the. So let's see that in action. That sounds kind of strange. Give me just a moment here to call that up. In this particular diagram, we've got router 3 advertising its serial 0 interface as a next hop to router 1. If router 1 takes the contents of that update and then advertises them to router 2, you must keep in mind that the next hop IP address is still going to be the same. It's going to be the next hop of router 3's serial 0 interface. So if router 2 in this particular case does not have an entry in its routing table for that serial network, router 1's got to tell router 2, hey, I'm your next hop. Otherwise, as we just went through, the route will not even be entered into the BGP table. So let's take a look then at router 2 in this particular network. I think it's going to be different in what the next hop is. It is, but take a look at this this route. Let's run show IP BGP 3.3.3.3. And it's going to learn about it from a couple of different points, but the one we're really interested in is the one that's actually not the best path. But this is the advertisement that router 2 is getting regarding router 3's loopback from router 1. You can see it's 172 from 172.12.123.1. But notice what the next hop IP address is. It's 123.3. And it stayed at 123.3 because that's what it was when router 1 first got it, just like we saw in the diagram. And I want to go over that one more time here with you. Router 3 advertises its loopback to router 1. And the next hop IP address is going to be router 3's serial interface. No problem there. But what you got to keep in mind is that when router 1 turns around and advertises that to router 2, the next hop IP address stays the same, because the route was originally learned about from an eBGP neighbor. And that's why we have to be so careful. I was saying earlier in this video, we've got to be so careful about noticing whether a neighbor is an eBGP neighbor or an iBGP neighbor, because come exam day, it's going to be a vital point for you on questions like this. Well, what is the next hop? And then when you're out there working on this in production networks, you've got to be able to look at a routing table like this and say, when router 1's advertising this to router 2, why is the next hop still router 3's address? How's that getting there? It's getting there because this route was learned from an eBGP neighbor and then advertised to an iBGP neighbor. In that circumstance, the next hop IP address will remain the same.